today is Fermion coupling to loop quantum gravity. Fermion coupling to loop quantum gravity, and this is in collaboration with Professor Lewandowski. Okay. So over the last decades, loop quantum gravity has been well developed. So there are those canonical approach, so spin-form models, and also group field theory, and so on. And actually, in loop quantum gravity, we have achieved a lot of achievements. So for instance, we defined a well-defined kinematic Hilbert space. And also in loop quantum gravity, we solve the Gauss and the diffeomorphism constraint explicitly. And those constraints, I mean, the gauge transformation and the diffeomorphism transformation is realized as a unitary operator in this kinematic Hilbert space. And also we defined a family of operators which represent geometric observables like area of two sphere, area of two surface, and volume of some three regions, and also the length of some edge, and also curvature. And for some of those operators, it has been well studied, and it turns out that, for instance, the volume operator and the area operator, they have discrete spectrum. Also, the dynamics of the loop quantum gravity has been also studied, although it is still an open issue. So for the dynamics, so we quantized the Hamiltonian constraint operator. And in the spin-form model, the transition amplitude has been defined. There are also the attempts to analyze the dynamics. And also we did the semi-classical analysis. For instance, we do the coherent with someone introduced the coherent state system in the canonical and covariant models. And also in this spin-form model, people do this large limit analysis and found that this transition amplitude gives us the effective Regulator calculus. Also, loop quantum loop quantization method has been used to those symmetry reduced model like cosmology and black hole models, and by applying the loop representation. So in cosmology, we get this famous result like the big bounce rather than big bang, and also the black hole to white hole transition. And also we found the black hole, so the discreteness of the black hole mass spectrum. And for those achievements, you can, I think you can always find the papers from those peoples. But according to the classical theory, our real world contains not only space-time, but also matters. And space-time tells matter how to move, and the matter tells space-time how to curve. And the loop quantum gravity as a quantum theory set a stage for incorporating the matters into quantum space-time. So there have been works to study this issue. For instance, there are those works to study the massless scalar Klein golden field coupled to LQG, and also dust field coupled to canonical LQG. And in the spin-form model, so one also can see the minimal coupling of Fermi and Young-Mills field to the spin-form model. And in our work, we are concerning about the model of loop quantum gravity coupled to Fermion field. And this has actually also been studied. So by employing those procedures proposed by Tiemann in 98, So in our work, we solve the Gauss constraint explicitly, and also we regularize and quantize the Hamiltonian constraint by introducing the vertex Hilbert space. And for this vertex Hilbert space is actually a key point in our work. And the vertex Hilbert space it is a Hilbert space group averaged with respect to diffeomorphism, preserving some specific vertices. And we will see the details later. But the motivation of this vertex Hilbert space is as follows. So the vertex Hilbert space was introduced for the model of the gravity coupled to massless scalar field. So the point is like usually in loop quantum gravity theory. So a graph changing Hamiltonian operator is usually defined at the limit of some regularized Hamiltonian operator as the regulator approaches zero. So in the quantum theory, we also need to define this limit, and in order to define this limit, so we introduce the vertex Hilbert space to remove the regulator and define this limit, and also the operator on the Hilbert space on the vertex Hilbert space carries the diffeomorphism covariance feature. This is another advantage to introduce the vertex Hilbert space. So now let us go to the details. So for the classical model of gravity coupled to Fermion field, so actually there are like two models. The first is that the Fermion field coupled to, so what I call the first order Fermion action. So it means like this action is a functional of this SL2C connection. So the fermion just coupled to this SL2C connection. And also there is this second order formulation. So for the second order formulation, the action is just a functional of the tertiary and also the Fermion field. And this connection is actually defined as the one compatible to this tertiary. So the fermion just coupled to the spin connection compatible with E. So in our work, so in this framework, actually there is no torsion involved. And in our work, for simplicity, we just consider the second order formulation. So the regular Hamiltonian analysis tells us that in the Fermion field, the canonical momentum is actually square root of Q multiplied by precise dagger. And precise Q is the special metric. Yeah.
Three-dimensional.
Yes, three-dimensional metric.
But it could be electric charge.
Yeah, so precise is the, so this Q is the, so Q is the determinant of the special metric, and this precise is the Fermion, it's a Fermion field on the initial slice. But in our model, this Q, rather than just some classical variable, it is actually an operator. So we hope that in our quantum theory, this equation pi equals to square root Q multiplied by precise dagger also satisfied in this quantum theory. But because this Q becomes an operator, then there will be some contradiction. So this contradiction is here. So for instance, if we consider the commutator between pi and f of a, so this a is just the variable conjugate to pi. So if we consider the commutator between this pi and this f of a, then it is 0 on one hand because this pi is the degree of freedom of the Fermion field, but this f of a is just the degree of freedom of the gravity field. But from the other hand, on the other hand, if we consider the dagger of this commutator, we will find that it is actually not 0. So there will be this contradiction. So in this theory, and this contradiction appears in our model just because in our theory, so this square root of Q is an operator rather than a classical variable. To solve this problem, one proposed this half density to define this precise tilde as this Q to power 1/4 multiplied by precise. And then
in what way does it solves this commutator problem?
Which one?
Okay. Why psi tilde is better than psi untilde?
Yeah. So this is the point. Because we introduce this precise tilde, then classically, rather than this equation pi equals to square root of Q multiplied by precise dagger, so we will just have this pi tilde. So which conjugated to precise tilde is just to precise tilde dagger. So this equation pi equals to square root of Q multiplied by precise dagger is actually disappeared. So we have this equation pi tilde equals to precise tilde dagger. So then we just don't need to realize, we just need to realize that the classical equation pi tilde equals to precise tilde dagger in our quantum theory. Then this contradiction disappear. Yeah. Okay. And then we just need to do the canonical analysis. We will get that the classical phase space is coordinatized by those three pairs. So A, E, C dagger, and nu dagger. So here A is just this Ashtika connection. It is an SU2 connection on the special manifold. And this E, we call this densitized thread. So because this E is actually a vector field of SU2 Lie value with weight 1. And here, so this Kasi and this nu, they are just the they are this precise minus and the precise plus. Here, this precise minus and the precise plus is the eigenstate of gamma 5. So that means like they are the left cavity. They are the Fermion field with the left cavity and the right cavity. So in our work, actually, we just consider, because we consider the massless Fermion field, so we actually consider the well Fermion field. So we just consider this Kasi. And for this nu, so it is just the seam treated as the Kasi. And then we have this Poisson bracket relation and the anti-Poisson bracket relation. So they are given here.
A question. So if we consider two fermion fields, we have to replace the Poisson bracket by this
Anti, yes.
And what if I want to have relation between non-fermion with fermion? Then what kind of bracket?
Okay. Yeah. So there are actually those formula about those. Yeah. So how to say? So there are those formula on how to define this Poisson bracket between. Yeah. So I think it's like. So where it is. Yes, but I didn't remember exactly. But it seems like so. Okay, so in some framework, so someone just unify this Poisson bracket together and also call it the Poisson bracket. And so here is like f of A and f of B. And AB is, they are just a bosonic variable or fermionic variable. So okay, so the point is like for those bosonic variable, so they are actually the they are actually the variable with grid 0, and for the fermionic variable, they are grid with 1. I think they just defined this Poisson bracket as the usual one, just like partial f by partial a, partial f by partial b minus partial f by partial b, partial g by partial a. Yeah, but there will be some minor sign here. So depends on the grid of those variable f and b, f and g, and also a and b, and also put a minor sign here. So there is also some, or maybe just put some minor sign here. So this minor sign depends on the, so what they call the grid of those f and the g and b and a. Yeah, so maybe here it is depend on the grid of a and b. Yeah, so whatever, so they just add some minor sign here. So depend on the, yeah, so to use this uniform formula to define this, yeah. So, and actually you can use this formula. You can use this formula to calculate the Poisson bracket between two fermionic variable. And you found, so on the, so by using this formula, this minor sign, because there is also another sign here, it becomes a plus sign. Yeah, but I didn't remember exactly what this sign factor here, but there are those formula like this.
So the conclusion is that one variable is bosonic and one fermionic, then what do we obtain? What do we obtain?
I think it is just the minus one. Because here, so the point, okay, so I think the point here is like if A and B, they are fermionic, so you just change the order of two fermionic variable, so you will get a minor sign here. But if one is fermionic and the other is bosonic, and you change the fermionic, the order of fermionic and the bosonic variable, then it seems like there isn't any extra sign, so it should also be minus, I think. But I need to check, so I'm not very sure. Yeah, so I think it's, so this minor sign just depend on, so if you change the order of fermionic variable, or you change the order of the fermionic variable and the bosonic variable. Okay, so these are the Poisson bracket. So now let us go to the dynamics. So the dynamics of this model, is governed by three constraints. So the first is the Gaussian constraint, which tells us how those variable get transformed, and the other is the diffeomorphism constraint. So it tells us that the diffeomorphism transformation of those variable will not change the physics.
So here you have both the fermionic variables.
Yes. So.
But upstairs there is only one fermionic variable in the Gauss Constraint.
No, there are two.
So
you can see there is this Cassie dagger. Oh, so you mean, okay. So you mean this percent and nu? So here I have Cassie and nu, but here I only, oh yeah, you are right. Yeah, so here there is also some like a plus nu dagger sigma nu here. So I just forgot it, sorry. Yeah, so for this is the full version of the diffeomorphism constraint. And the dynamics of this model is is actually encoded in the Hamiltonian constraint. Okay, so now let us go to the quantum theory. So in the quantum theory, so we need to quantize the gravitational sector of this model and also the Fermion sector of this model. For the gravity sector, so it is just a quantized at Euro in loop quantum gravity. So we first need to give a graph, and with respect to this graph, we define some Hilbert space, and this Hilbert space is isometric to some SU2 to this power. So this power, this absolute value of the E gamma actually means the number of edges in this gamma. So, and this d mu h is the higher measure on this SU2 to this power E gamma. So in this Hilbert space, there are two operators. The first is the multiplication operator. So this is something like this X operator in the quantum mechanics. So they just act as the Euro multiplication. And the other is the derivative operator. But unlike this quantum mechanics, so in quantum mechanics, we just have one derivative operator because this is an abelian group. But here we have non-abelian group. So we have this left and also vector field on SU2. So we actually have these two derivative operator. And I think so you can, if you want to learn loop quantum gravity, you can just remember this picture. So this is the fundamental, I think this is the fundamental operator structure of loop quantum gravity. So for each edge E, we actually have three operators. So the first is the holonomic operator, the multiplication operator, which locate on the edge. And also there are two derivative operator. So one locate at the starting point of this edge, and the other locates at the ending point of the edge. And the physical meaning of these three operators are the following. So for the holonomic operator, they are actually the parallel transpose from V1, from this vertex V1 to the vertex V2. And for this flux operator, so what we call this G flux operator, so they have the physical meaning like the area vector at this vertex V. So you can imagine that as for instance, at the starting point of this edge, there is a surface, there is a two surface, and the area vector. So a vector to interpret the area of this surface is this G operator. Okay, and for the Fermion field, so before quantizing the Fermion field, we need to first to do the simulation to this classical Fermion field. For instance, we have this Kc, and actually this Kc is this half density. So in order to smear this Fermion field, so someone just proposed this square root of delta. Actually, inside this square root is actually the delta function, and as we know, this delta function is some scalar field of density 1. So if you do the square root of this delta function, so you will have some natural scalar field of density half. So this is density half scalar field, and also this Kc is a half density Fermion field. So multiplying them together, you will get some field of density 1. So you can do this integration. So independent of the background. So you can regard this.
So you say that chi is the Dirac delta.
No, chi divided by this epsilon 3. So
regularized.
Yeah, regularized version of this delta function. Yes. Okay, so you actually can regard this mirroration as a canonical transformation. So you can just calculate the Poisson bracket between this theta, between those theta field. You will find that the Poisson bracket, the anti-Poisson bracket between those theta field. So they give us this delta xy. So this delta xy now is canonical delta rather than the Dirac delta. So if you use this Cassey field to do this Poisson bracket, you will get the Dirac delta. But here, because of this simulation or because of this canonical transformation, so this Dirac delta becomes canonical delta. Canonical delta. Yes.
And this is independent of the choice of this regulator?
No, not really. So actually, so this is the point why I write this, it is here. I think it depends on this regulation of the Dirac delta. So at least if you want to, if you want, yeah. So at least if you choose such a regularization of this delta function, so you will get the Poisson bracket between this data function. So yeah, so this is just used to do this derivation. Okay. And then we just need to quantize this algebra. So this algebra of zeta rather than the original algebra of Cassey. So the Hilbert space is the following. So the Hilbert space of this system is actually labeled by a set of vertices, and the Hilbert space labeled by this set of vertices is just the tensor product of the Hilbert space at each vertex x, and at this each vertex x, so it is just a finite dimensional Hilbert space, which is spanned by this four orthonormal bases, and inside and on this Hilbert space HXF, so the Hilbert space at each vertex, we have those ladder operators, zeta and this dagger. So for instance, so if we use this zeta dagger acting on this state 0, I, 2, so it will change 0 to be 1. But if we use this zeta dagger minus 1/2 to act on this state, so we will get an extra factor. So it will change this 0 number to 1, but there will also another extra sign factor. So just because here we can see that the Fermion field. So once you change the order between this operator and also this number I, so there will be some extra factor here. Okay, so here is this Hilbert space, and now I'm going to compare this result with this lattice QFT. So actually, so here in our system, we have the Hilbert space, which is the Hilbert space of the gravity and the Hilbert space of the Fermi. And then we have this operator, data. And in the quantum field theory, so if you are familiar with this quantum Fermi field, so you will know there they have this operator, this ladder operator called A, and also the ladder operator called B. And the relation between our operator and the operator in the quantum field theory is that so they are the same up to Bogoliubov transformation. And and here this coefficient of theta is actually some, so it's defined like this theta multiplied by the exponential ikx diagonalize the effective Hamiltonian. So here by effective Hamiltonian, I mean I mean the following, because here, so in our Hamiltonian, so we have this quantum, we have this Hilbert space with respect to the gravity, and also the Hilbert space with respect to the Fermion field. And if we choose, for instance, some coherent state in this gravitational Hilbert space, so then we just need to use this background state to sandwich this Fermi Hamiltonian operator, because in this Fermi Hamiltonian operator, it involves the operator of those loop quantum gravity operator. So you just need to use the background to sandwich this operator to change those gravitational operator to some regular number. Then you will get this. You will get an operator in the Hilbert space of the Fermi field. So this is what I call the effective Hamiltonian. And this is actually a procedure to reproduce the regular quantum field theory from our framework.
So what is this Bogoliubov transformation? You say it somehow is implied by the
effective Hamiltonian.
By the gravitational interaction. Effective Hamiltonian.
Effective Hamiltonian is like so here in our theory. So this Fermi Hamiltonian contains not only the operator of the Fermi field, but also the holonomy and the flux. So they are operator. So, but in quantum field theory, so this background variable, so they are actually classical. They are actually classical variable rather than this operator. For instance, if you consider the Fermion field in Minkowski spacetime, so this metric is just a classical Minkowski metric rather than the metric operator, right? And if you consider the Fermion field in covered spacetime, and then those background variable, they are also this classical variable rather than operator. But in our theory, so this background is interpreted by operator. So in order to change this operator into the regular C number, so we need to choose a background state, which probably should be coherent state, so that it resembles the classical background. And we just need to use this background state to sandwich the Fermi Hamiltonian, to change the operator involved in the Fermi Hamiltonian to classical number to get this effective Hamiltonian. And then this effective Hamiltonian is just some Hamiltonian in the Fermi Hilbert space. And okay, so once we get this effective Hamiltonian, we need to diagonalize it. And this theta is actually related to the eigenvector of this effective Hamiltonian. Okay. Okay, so now let us come to the so can I move this one? So now let us come to the Gauss constraint of this model. So for the Gauss constraint, it is actually the plus of two terms. One is the Gauss constraint of the pure gravity system. The other comes from this Fermion field. So first, let us consider the geometric meaning of these two parts, these two terms. So for the first term, as I said before, this flux operator have the geometric interpretation of the area vector of some area due to this edge. So for instance, if we consider a graph, a 4-valence graph, so this is the vertex and there are these 4 edges. So due to each edge, there will be some surface, and the first term of this Gauss constraint actually means the plus of those area this area vector of those surface due to each edge. And for this, for the second term, so this operator f, so you can interpret it as the spin of some Fermion particle, and this Gauss constraint just means the summation of those area operator due to this edge, and also the spin of this Fermion article, and so you just need to study the explicit expression of this operator f. You will find that this f actually perform just like an angular momentum operator, and if it acts on the state 0, 0, and 1, 1, so they just get the result 0. And if they act on the basis 1, 0, and 0, 1, so you can see actually so the second equation means like this 1, 0 and 0 and this 1, 0 and this 0, 1 basis is just like the the 1/2 angular momentum Hamiltonian, and so this 1, 0 is the spin up state, and this 0, 1 is actually the spin down state, and this operator f is just the angular momentum operator. Okay, so the Gauss constraint tells us that the summation of this g and also this f is 0. So what that means? So that means like we will have, okay, so here it is like the decomposition of this Hilbert space at the vertex v. So we have this 0 spin Hilbert space, 2 0 spin Hilbert space spanned by 0, 0 and 1, 1. We also have a half spin Hilbert space spanned by 1, 0 and 0, 1. Okay, and according to this result, so we will have 2 types of this Hilbert space. So the first one is that, so we just choose this 0 spin Fermi Hilbert space. Then what we will get is actually the summation of this G operator equals to 0. And what I see here, that means like the area vector of those surface due to each edge is actually 0. So then that means like we will get a closed tetrahedron. So because we have the area operator of those surface, the summation of the area operator of those surfaces is 0. So that means like we will have a closed tetrahedron. But for the second one, it is different. So for the second one, that means, so the second type Hilbert space is that we choose this half spin Hilbert space combined with this gravitational Hilbert space, and then that means like the summation of this area this area vector is no longer 0. So they are just something like they are no longer 0, and you need to plus the spin of this Fermion particle. So together they are 0. So it gives us this geometric picture like this. So we will have, rather than a closed tetrahedron, so there will be a Fermion particle. So there will be a Fermion particle. This you can regard it as a hole on this surface. So the area of those surface, the summation of the area of those surfaces is no longer 0. You need to consider the spin of this particle. And in the quantum theory, explicitly, so for this type of state, it is actually given by the following quantum number. So we need to have like 4 spins on the edges, and also an intertwiner at the vertex. So here, because the spin of the Fermion particle is 0, so we only need to consider the intertwiner of this gravitational Hilbert space. So this is SU2 invariant vector on the tensor product of this Hg. Okay, and we can see, as I said, those spin G is actually means the area of those surfaces due to this edge. Then this intertwiner actually have the geometric meaning of the shape of this tetrahedron. So this is like what this Gauss constraint tells us. So we have like a 4 quantum number to tells us the area of those surfaces, and also the intertwiner at this vertex to tell us the shape of this tetrahedron. And for this one, so this intertwiner is no longer just inside this Hg, but also you need to consider the invariant operator in the Hilbert space Hg times this HF. So then this is just an intertwiner with an actual index. So you can see here it is an intertwiner with 4 index, but here it is an intertwiner with 5 index. And the last index means like this index comes from the Fermion Hilbert space. Okay. So now let us come to the Hamiltonian constraint. So classically, we have this smeared Hamiltonian constraint, which is smeared by a Laplace function n. So it takes the following form. So here, this function h is actually a function of the arithmetic connection, the density, the densitized tertiary, and also this field C. But in our theory, so we actually don't have this operator directly correspond to those variables. So the elementary operator in our theory is this Holonomic operator. It is actually the integral of this A along some edge, and also the flux operator. It is actually the integration of this E on some surface, and also the smeared version of this C, this zeta. So we will have those elementary operator rather than this variable AE and C. So this cause a problem in loop quantum theory. So whenever we want to quantize some value to operator, so we need to first regularize this classical expression to get an expression in terms of those variable corresponding to this elementary operator. So we first do this regularization to get some function, which is actually the function of Holonomic, the flux, and also this theta. And then we can just replace this classical variable to this operator and get this quantum operator. So this is actually what we do in our Fermion theory. So this is the final result, and I'm not going to write the explicit expression but just some general expression. So this will be enough for our talk, and I think it is also easier for people who are not very familiar about this. And here, and in the following talk, so here, so you can see this Hamiltonian operator is actually the limit of this regulator d delta go to 0, and there are these two terms. And for the first term, it is the summation of three other terms. And in this talk, I will just choose this typical term H1 as an example to see how we do this work.
And there are some, I'm studying the structure of parentheses. Are there just missing two parentheses?
Oh, yeah. So there is something. Yeah, here it, and also this one. So, yeah, sorry. Yeah. Yeah. Okay. Okay, so for the first term, H1, so it actually acting on the state like this. For instance, I have a 4-valent graph, and at the vertex V, we have a particle, we have a Fermion particle with a spin. And then if you use the operator H1 acting on this state, so the result will be the following. So the operator H1 will move the operator of this H1 delta actually. H1 delta will move this Fermion particle at the central vertex to some edge, and the length of this Fermion particle to this vertex is now delta. So this delta actually means the length of this part of this sector of this segment of this edge. Okay, and this is the result of the action of this H1 delta on this state. And then there will be two problems. So in our work. So the first is to define the limit delta goes to 0. So because originally this operator is actually the limit of delta to 0 something. Yeah. So the first problem is how to define this delta 0. And the second problem is actually concerned to the adjoint of this H1 delta, that H1 delta dagger is not gauge covariant. So let me explain these two problems. So for the first one, so the point is like, if you consider the inner product between this state and this state, the difference of these two states is like one is the length of this segment is delta. The other is the length of this segment is delta prime, and the delta is not equal to delta prime. So if you consider the inner product of these two states, so they are just 0. That means like these two states with different delta, so they are orthogonal to each other. And because of this, so the limit of this delta to 0 cannot be well defined. Yeah, because you just use this delta to act on this state, you will get some state. But if you change the value of delta, so you will get some state which is orthogonal to the previous one. So that means like the limit of this operator cannot be well defined. So this is the problem. This is the explanation of problem 1. And for the problem 2, so if we consider the adjoint of H delta 1, so you use the H delta 1 dagger to act on this state with this parameter delta. So you will get you will just move this Fermion particle again to the central vertex. But if you use this H delta to act on some state which have a different parameter. So this delta prime is not equals to delta. Then the result will be 0. That means like if you consider the left-hand side of these two states, they are actually diffeomorphism equivalent to each other. But after acted by this H31 dagger, so the result is no longer diffeomorphism equivalent to each other. And this is what we mean that this H31 dagger is not diffeomorphism covariant. Sorry, so here gauge means diffeomorphism gauge. It is actually not diffeomorphism covariant. Okay, so but how to solve these two problems? So the strategy to solve this problem is to introduce this vertex Hilbert space. The idea of this vertex Hilbert space is just that you define a Hilbert space on which, so those states with different parameters, they are just equivalent to each other. So in this H Hilbert space, in this vertex Hilbert space, so those states are equal. And this Hilbert space can be defined by the group everything with respect to diffeomorphism preserving V. And because by this definition, so this vertex Hilbert space is actually just a Drew space of this cylindrical function space. So the cylindrical function space means some dense subspace of the kinematic Hilbert space. So we just to use the Drew space of some dense subspace of the original kinematic Hilbert space to study our model, and then everything will be well defined by the duality to this H vertex. So this is just some details, but I think the most important is this basic idea to identify those states with different parameters. And then let us see how these two problems are solved. For the first one, so rather than consider, so here, let me see. Yeah, so here there is a prime here. So prime means like we consider the Drew operator in the vertex space, because I said here, this vertex Hilbert space is actually a Drew space of the original Hilbert space. So in this vertex Hilbert space, rather than consider the original operator, we need to consider the Drew of the original operator. And then the Drew of this original operator will be well defined in the Hilbert space, just because, so if we consider the, yeah, so it is like here. So because we have identified those states with different parameter. So actually the Drew space, the Drew operator acting on the here, yeah, here. The Drew operator acting on this state is the same as the original operator acting on the state. So this is just the difference of the definition, but the result is the same. And because we have identified the right-hand side of the result in this vertex Hilbert space, then there will know this relation like the right-hand side of this result are orthogonal to each other sometimes. So they are just identified. Then that means like this H31 prime, this H31 is equal to H30 prime 1 and so on. So the limit of this operator as delta approaches 0 will be well defined. And for the second problem is actually a little tricky. So this H31 dagger is not diffeomorphism covariant actually means like this H31 dagger cannot be promoted as an operator in this vertex Hilbert space because the right-hand side of this result are not equivalent to each other, but the left-hand side are equivalent to each other. Then that means like this H31 cannot be promoted as an operator in this vertex Hilbert space. So the solution is just to give up this operator H31 dagger. So we just don't consider this H31 dagger in the vertex Hilbert space. So we just consider so because we know that this H31 prime has been well defined in the Hilbert space. So rather than consider the jewel of this H31 dagger, we just consider the dagger of this H31 prime. So then this problem 2 is also solved. Okay, so at the final result, so we will get two operators like this. So the first one is like to move this Fermion particle to some edge here. And here, the length of this edge in this vertex Hilbert space is no longer important because the length of this is actually doesn't have any physical meaning. So we don't need to consider the length of this segment of this edge. So this is like the acted by this operator H1, and this H1 prime dagger just move this particle back to the central vertex. Okay, so this is intuitively the result, but so what will happen if we consider if we add those quantum numbers on this graph? So for this state, as I said before, so there are those quantum numbers like the spins, which has the meaning of the area of those of the surface due to edge, and also the intertwiner means the shape of this tetrahedron. So acted by this operator H31 prime, so it will first move this particle to the edge, but also change the spin on those edges, and also change the intertwiner.
So are you saying that the spin changes on all the edges are not only on the one edge?
Okay, so that is a good question. I think it depends on so here I just give some general equation. So depend on the explicit expression of this H1. So it could be just change the spin of this edge.
Is it possible that the spin changes to 0 on the surface?
Sorry?
So it is possible that the new spin becomes 0 on this edge.
It also depends on your definition. I think it also depends on your definition. Of course, for instance, if you choose this G1 to be 1/2, right? And in this operator, you also change the representation of this polynomial to be 1/2, then it can be 1. But you can also, by definition, for instance, when this spin is 1/2, you just choose the representation of the polynomial in your operator to be 1, and then there will no 0 appear here. Okay, so what does that mean? So that means actually, so first this operator move this particle from this vertex V to the edge, and also change the spin and also the intertwiner on those edges. And as what I said before, the spin and the intertwiner tells the shape of this tetrahedron. That means the metric of this tetrahedron. And then this gives us a picture that this operator will first move this particle, but also change the metric of the background spacetime. So this is something like the interaction between the particle, the Fermion particle, and our background and our space-time background. And this is the same. So it just move this particle back to this vertex V and also change the spin and also the intertwiner. Okay, so finally, so let me give the conclusion of my talk. So first, our work considers the coupling model of Fermion field to canonical loop quantum gravity, and we investigate the Gauss and the Hamiltonian constraint in this model. And we solve the Gauss constraint explicitly and regularize and quantize the Hamiltonian constraint by introducing the vertex Hilbert space. And also, actually, this is an outlook actually which we have finished. So this framework can also be applied to recover the Euro quantum field theory on lattice, and then we can consider the back reaction between the quantum matters and also quantum space-time. So thank you.
Thank you very much. Questions?
So do you comment on the relation between Robert and T-mass per? So like what are the main differences and how is Robert an improvement of T-mass?
Okay. So I think the point is like in this kinematic part, so we just employ in this kinematic part like here. So we just employ the framework proposed by Tiemann. But for this kinematic part, for instance, for this Gaussian constraint, so we consider it explicitly and it tells us how it is solved in this framework. And I think the main difference between our work and the Tiemann's work is this Hamiltonian operator. So in this Hamiltonian operator, we defined a graph changing Hamiltonian operator by introducing this vertex Hilbert space. And this is not done by Tiemann. And actually, yeah.
More questions? Questions from people online, perhaps? Okay, if there is no more questions. Okay.
So
Correct.
What do the other operators do? Just
So you mean those operators?
Yeah, you discussed H1.
Yes, I discussed H1 because H1 is the typical term, and for the other operator, so they just so they just change. I think they just change the. So for this H1, so we can see it not only change the intertwiners, but also move this particle. But for the other part of this operator, so they just change the spins, and they didn't move this particle from the vertex to the other. Yeah.
Other questions? Okay, so we think again.